Okay, this video covers the Costas Loop Update Equations that I skipped over in class because honestly I wasn't sure where the square goes in the cost function. Okay, so we started with the cost function that's given by the expression below, where we look at JC of theta. Okay, so let me highlight that. JC of theta, I highlight that in green, is here, and so we're taking the average of the low-pass filter of the received signal times the local oscillator, low-pass filter, all that, and then square it. Okay, so to do the update equation, we need to take the derivative of all the stuff in green with respect to theta. Okay, so the way that goes is you start trying to interchange order of operations. So we're going to start out, we're going to interchange the order of averaging and differentiation. Both those are, we're doing averaging a finite number of samples, so we should be able to interchange that order. Okay, so that's our first step. So I go to here, average second, differentiate before you do the average. Okay, so when I'm looking at this derivative, I'm taking the derivative of the low-pass filter squared. So low-pass filter, all this stuff first and then square. So if you think about it, if you're applying the chain rule, then essentially the inside is all the stuff that has the low-pass filter on it. Okay, so I highlighted the low-pass filter in blue because that's like the inside derivative. So I bring the two down, I'm left with the inside, which is low-pass filter, and I just put a couple of quote marks and some pink shadowing here to show you just copy all this stuff right back into here. Okay, so 2 times low-pass filter, and then you multiply by the inside derivative. Inside meaning what? Well, the inside was the low-pass filter stuff. Okay, so d low-pass filter, d theta, that shows up here, so differentiate with respect to theta. And so what we then do is we push the derivative inside the low-pass filter. Okay, and normally you can do that. There could be some numerical problems if you have something that you're differentiating that's really noisy, but it turns out we can get away with it here, and in a practical sense this works. All right, so you notice here we're going to low-pass filter second, and then take the derivative of the stuff in the bracket here. Okay, so I'm now looking at the derivative of the stuff highlighted in pink, all right, which is up here. All right, so when I go down to the next step, I have my low-pass filter showing up, and then this derivative is, well, R of k is a constant, it doesn't depend on theta. Okay, and then we have, R of k, it does depend on an oscillator, but it's, the phase is phi, not theta. All right, so then R of k acts like a constant, cosine is on the outside, then we have the inside. All right, the inside does have a theta on it, so derivative of cosine is minus sine, so I get this minus sign here. And then the sine function. Leave the inside alone, so W naught k plus theta. And then we multiply by the inside derivative of the cosine argument, which happens to be 1 in this case. All right. So that essentially does it. We have the update equation. We take the average of this low-pass filtered piece times this other low-pass filtered piece. So if I substitute back in, this is my total update equation, where I have 2 different pieces. The average low-pass filter piece of cosine times R of k, and you multiply by R of k sine. All right. Okay, so we'd covered the code for this in class, and this is where the update equations come from. At this is the point actually where you can ignore the averaging, because the low-pass filters should have this changing slowly enough, and then you can also use the update step size to serve as a little bit of an averaging step.